Yeah, yeah. It just happens. That's nice. Yeah. Okay. Think we had enough time to try that exercise. It's okay if you didn't get it all the way. The tree is there for you to check it out if you wanted to do it on your free time. So it's going to change gears to more runtime application resilience. And in particular, I want to talk about one strategy that I find really useful. It's called basically building processes for dealing with separation of concerns and bulkheading the errors that happen on your system. So there are different scenarios for errors on runtime for sure. What happens when the database fails? What happens when the network fails? Your node runs out of memory. Does one exception in one component of your system affect others? Maybe, maybe not. The idea is, if for some reason your application is not performing the way it's normally performing, you want to make sure that the strain doesn't break down stuff that doesn't necessarily is related to that, right? You want to avoid what is commonly known as cascading failure. You don't want one failure here starting to propagate in an unnecessary fashion to the rest of your system. And being reliable is not so much to be able to deal with errors when the error situation is happening, because again, some errors are really difficult to mitigate, like things are down, you cannot do anything about that. But at least your application should be able to go back to a healthy state without touching it after the downstream system is up again, right? A lot of systems don't do that. A lot of systems get hanged and suddenly they become unresponsive because they're waiting for answers that are never going to come on requests and stuff, right? So the first approach, which is a no-brainer in Haskell for dealing with containerization of errors, is using async threads for different parts of the system. And if one of the exceptions happens on those threads, it's not gonna it's not gonna stop the other threads from running, right? That gets you so far though. If one exception is thrown on one of the threads, the thing stops, assuming the thread that just stops is consuming a queue that another thread is putting values into. Your system is going to die eventually, right? If a process dies, what's next? You can do something pretty naive, like having an async that wraps another async, and as soon as it sees failing, it just reruns it again, right? But having these strategies in code is really non-flexible. Like there's different use cases, different scenarios where you want to do different things are sensitive. And writing down procedural code to deal with this is a big no-no. Yeah, depending on the run subsist that you're doing on your subroutine, things might be different, right? And also, there's no telemetry out of the box. Like you will actually have to go and add the logs yourself to figure out what's going on in the system. There's another language that did this pretty well, and it's called Erlang. Erlang and the actor system, they have this concept called supervision trees. Raise up if you have never heard of supervision trees. Okay. So the way it goes is supervision trees do the algorithm that we were doing before, but they define semantics that are cover most use cases that you want to deal with, right? So instead of talking about a procedural algorithm, you talk about a strategy. You say, I want this strategy for restarting an application, and there's certain guarantees about that strategy, right? And it's a configuration value. It's not a procedure.
So, OTP supervisors end up having configuration, but at root, how are they different than a type class?
type class?
I mean, in Haskell land, why wouldn't you just have your OTP supervisor strategies defined as classes?
Because it's I don't know how to answer that question. How do you use type classes to, like you would say something around like the function that we were having a second ago.
Or I guess I mean with components, like, yeah, with restart strategy, and then parameterize that by a restart strategy.
Yeah, you will have a function as a thing that you can use, right? That's an approach. Yeah, that could work. And you can have a type class, but it's not impossible. No, it's okay. It's not impossible. I didn't go through that path though.
Okay.
So we have static values that represent restart strategies, and we just specify those on a configuration setting. It allows you to, when you create a supervisor, you can have a bunch of workers being supervised by one single supervisor, and you can have behaviors like, say, all these workers depend on each other, so if one of them fails, fail all of them. Like that's what async does by default when you run concurrently. When you say run concurrently and you have a bunch of async values that you want to run at the same time, if one of them fails, all of them fails, right? So that's one strategy that works really well, and that's a way to have a high order function to manage that, right? But sometimes you don't want that. Sometimes you just say, well, these guys don't depend on each other, and if this guy fails, just restart it. Like you don't need to shut down the other end to make my system reliable. Once you start to have this concept of supervision tree, you can imagine that tree, that trunk, being part of a bigger trunk, right? So you have a supervisor that is supervising a bunch of workers. If for some reason the supervisor failed because there's a lot of failures going on from the workers, that can propagate to a bigger supervisor, right? So you can start building trees of components that you can restart in different fashions. And this library in particular keeps telemetry of all the things that happen. If a thread fails, it's going to tell you, hey, this thread failed with this error. This thread that you named blah failed with this error, which is pretty helpful to know what's going on. There's two restart strategies that you have to be mindful of. You have workers and supervisors. Workers are threads that are going to be running forever, right? Most of times. And they can have three different behaviors. They can either be running forever because you want them to run forever. It's like reading from a queue and executing a job, and it never stops. You have something that is transient, meaning only restart this thing if it fails. If it doesn't fail and it ends, that's a normal behavior that I'm expecting out of the system, so that's okay, don't restart it.
Does permanent mean normal termination and failure termination?
Yes. So if the algorithm finishes successfully in any way, it just builds it up again. Transient is only do that if it is a failure. And temporary means do the same behavior as fork.io. If it fails, If it doesn't fail, like you really don't care about that point. That's for workers. For supervisors that are monitoring many workers at the same time, you have a restart strategy there. You can say, if one of the nodes fails, I want to just restart that node. So in this example, if number 2 fails on that tree, the one that is red, just restart it and leave everything as is. The one for all means if one of them fails, all of them fails. Restart all of them at the same time. And there's one more that is called one for rest, which keeps an order. So you have 1, 2, 3, 4. If 2 fails, then 3, 4, 5 are gonna be restarted as well. But only like if your predecessor fails. 1 is gonna be intact. That's how one for rest. It's not implemented in this library yet. And that's more or less supervision trees in a nutshell. How we do this with Haskell, let me show you. Capatas mean 4 men in Spanish. Let's go to the documentation page. So this is not what I wanted. So the way it works is I want to be able to replace every place where I do fork IO or async with a call that receives this metadata and performs these restart strategies. To do that, I just create a Capatas, which is the root supervisor of all the system. I specify a name for it, and I have a way to set options to it. If I don't want to set any options, I just use the ID function there. Once I have that, I can just say fork worker. And the worker is going to have different options that you can use, right? Like you have a name for the worker, which is going to be used for telemetry purposes. You have an action that you want to execute in this worker, an IO action, or a monitor. Like at this point, the library supports monad transformer stacks, so it could be any monad. But it's something that is going to be executing, right? And you can, as a third argument, set different arguments to it. So in this particular case, we're setting the work restart strategy to transient. Okay, sorry for the size. And normally what you would do if you were running fork IO is doing fork IO with my useless worker and nothing else. What changes? You need to have a supervisor to create the thread, and you need to specify the options for both the supervisor and the worker. With those in place, you have a worker that can run permanently in case of failures. That's for replacing fork IOs with fork workers. You have a way to say, I want the supervisor, like it makes sense for this supervisor to just have a bunch of workers embedded in it. And when I start a supervisor, I want all these workers to get started automatically without having to do fork worker. That's what a static supervision tree means. It's more or less the same as building a fork worker. You just build what is called a worker spec with the same parameters. And you have a way to say, this supervisor is going to have this worker specs. This worker spec is not necessarily for workers. It could also be supervisors. So if you have a supervisor spec, and you set that as an entry that the main root supervisor needs to start, it's going to start all of that as well. So you can hide out supervision trees architectures and put that on a bigger supervisor. And that way you can compose supervision trees together. There's also a way to, again, create a supervisor in the middle. Like you have the root supervisor and you have the workers. You can have a middle supervisor in here for whatever reason you need to. For that, it's more or less the same. You need the Capatas. You need to do fork supervisor with the supervisor options. And in here, for example, we're saying that the restart strategy is all for one. You don't specify any IO action. You just say what is the metadata for the supervisor. And then you just do fork worker with that supervisor, and you build a sub-branch, right? You can do that with, again, creating a static supervisor with supervisor spec, and then just passing that as something that your root supervisor needs to start up. Enough code without running. Let's look at some of that. So let's go with a simple example first. This is an implementation of an algorithm that creates a group of threads that just prints numbers to a standard out. So you have a process, a batch process, right? Like why is this useful at times? Imagine that you have a long-living process that is being run by your Haskell program for some reason. Like you need to run a server. Like in one instance, for example, we were running Phantom.js instances with the binary so that we could delegate some responsibilities to Phantom.js through a socket. And our program was responsible of the life cycle of that Phantom.js process automatically. You want to have that on a thread. You want to have the process dedicated to a thread. And if that process fails, I want the thread to fail and get restarted again. This algorithm does something similar to that. We have a process that prints through bash a group of numbers on the terminal. And we're going to have another process that just performs random kill statements into the bash process. And as soon as those fails, I want those number printers to get back up. Right? So this is the logic on how it goes with async, which is not that very interesting because as soon as you run this, it's going to stop working after a while. Sorry. Yeah, should be load. Main. Oh, proc number, of course. So if I say I have 5 proc numbers, whoa, okay. So we're having a bunch of processes running, and there's another thread that is killing the processes one by one, right? And you see that the numbers of processes running start to reduce. Now it's 2, started with 5. Now it's just a single one. So, okay, we see that we are not able to accomplish what we want to accomplish with just async. If we use Capataz, how that would look like. So we have the same algorithm span number process. It's the same IO subroutine that we will use on an async. This is not the one. Example 1, example 2, main. There we go. We fork the original Capataz supervisor, and then we do a bunch of fork workers, the same way we were doing async before. The logger options, it's been built over here. I say build log worker options with the log options. Oh, never mind. This guy has a thread dedicated for logging, and this is a worker spec for the logger thread, right? So I have a logger, a thread dedicated for logging purposes, and I want my log func that I'm creating sending those messages to that logger thread. The important bit, though, is this bit over here, where we have a build worker options with the worker prefix, the algorithm that we were using before, a span number process with a number of processes, and we say that all of them are permanent. We go and fork worker of all of them, and then we're going to have another worker that is the killer thread, and we're going to do that as well, another fork worker for that. Finally, we're going to say we want to join to the thread of the main supervisor so that it blocks. And if there's any exception or exiting, it's going to terminate the Capataz thread with all its states and all its supervised threads, and it's going to return. How does this perform? Okay. If I go and do main, it's going to ask me the same thing. Proc number 5. Takes a while at the beginning. Okay, so we're having all the processes running. It's killing 3, 6, 30. It's being replaced by something else. And every time a thread kills one of those processes, the thread in Haskell is going to die, and Capataz is going to listen to that. And because you have a permanent strategy, it's going to restart them again, right? Any questions so far? The telemetry is going, that's a great question. When you create a Capataz record, the root supervisor, you have one option that says, take this callback and call it every time something happens. Capataz event happens. Capataz events is a worker got terminated, a supervisor restarted something, supervisor got from halting to halted. All these things that happen inside the system that you care about are being managed by that callback. And you can do whatever you want with that. You can say, okay, every time I get an event, if I know how the events look like, create in statsd register and count how many times workers get restarted. What is the ID of the worker? All those things are available through that. And right now what I'm doing is just doing a log debug in here, display. We are not seeing any telemetry from Capataz here because we are on info, right? But as soon as I change this to true, to have it verbose, and I start the system again, if I kill this, there we go, and reload, and execute. Oh, way more information. But it gives me, it's going to go, sorry. Okay, it's going to go up there. Start saying, okay, we have a supervisor that changed state from initializing to running. The supervisor spawned a new process. The Unix process Capataz supervisor spawned a logger with this UID. So the UID is always going to be the same. If for some reason the thread dies, this number is going to change. So right now it's 293. If that thread dies, it's going to change it with a new one. But the ID of the worker is always the same. So you can see, oh, I have these logs. I want to grep by this UID. You will see all the history of how many times it has been restarted. Yeah, like you can see how it spawns new processes. Does this 5 times. And then you have, oh, the worker number 3 died. And there's a callback that you can specify in the worker's settings, metadata. And you say, every time this worker fails, call this IO or this subroutine. This log is saying, hey, I called this subroutine and it didn't fail. And it's going to say, the process failed with that error. It tells you what the process ID is and what's the error that happened. Right? In this case, it's an exit 15. It tells you, well, the supervisor restarted the failed process. And now you have it again, worker 3 with the thread ID 314. And it keeps going. It's more or less the same thing, always. This particular problem is not interesting. There are really cool ways to use this API, though. I have a way to, by just defining a bunch of parameters on a function, to build a still worker pool that is completely supervised and error resilient. So, and mind you, this is not released yet. This is part of the bleeding edge. But let me get to that branch and show you, because I think it's pretty cool. Still worker pool. So you have all these options where you say, I have a subroutine that pulls work out of somewhere. What is that somewhere? It depends on your application. It could be SQS pool. It could be a Kafka stream. It could be a TQ. You made a decision when you partially apply the function and pass it over here. Then you say metadata for the supervisor that supervises the workers. What's the name? What are the options? What is the prefix of the workers that are going to be in this pool? How many of them do you want there? What is the action you're going to be calling? They're going to receive the worker ID for you to log anything with the same ID if you needed to. And the value that is being pulled out of the resource input. And perform some side effect. And also, I want options for all the workers that are in this pool. Right? And as soon as I do that, if I do something like this, where I have all these parameters set, I will have a supervision tree that looks like this, where I have a worker manager thread being supervised by my worker pool that pulls stuff out of the input source. And then I'm going to have another supervisor that is not dependent, that handles errors on the workers only, that will manage all the different workers. So by just specifying statically a value, I'm able to get this behavior for free. I just have to plug in the subroutines that give me the inputs and the outputs, the effects of the things I'm working on. And what is interesting about this algorithm is it starts with a pull with a queue from the manager, and all the workers say, hey, I'm ready for work. And the manager says, okay, I'm going to take the first one off the queue. There's some input here that I want you to work. Go work for it. As soon as you have that, once the worker is done with that, it's going to queue himself back saying, hey, I need your work. I'm not doing anything, right? And as long as there's input coming in and there's workers available, that cycle is going to keep going, right? And this is pretty cool because as soon as you have a source, say Kafka stream, and you want to distribute that through a bunch of workers, you just have to specify the two functions that matter: how you get the value in and how you do something with that value. All the mechanics of how you integrate things, it's just a declarative thing, right? I don't think it's worth going through the implementation of this, but I think it's more fun to look at examples using it. And I have an example here, which is a first iteration of one of the exercises we're going to be doing, which is a web crawler, right? So I want to be able to have a web crawler that, with the Genesis URL, has a bunch of workers that fetch each of the links that it finds, starts accumulating them in a queue, and pull them and keep aggregating, right? What we're going to do with the crawlers, like for every page that we are crawling, that's not defined in the algorithm. It's really easily extendable to add something like that. But let me show you how it looks like. So 162 lines of code. So there's this really interesting, like the most important function that I would say doesn't have to do anything with supervision trees whatsoever. That is fetching a list of URLs from a URL. So I have a request manager from the HTTP client library. I have a URL, and I can either return you a list of, either with a Unicode exception because the page that you're sending me, the page I'm pulling in from the internet is not UTF-8, or a list of links, right? So I go and parse the URL, perform a request, parse the HTML, and once I have an HTML, just look for all the anchors. These libraries are HTTP client, HXT, and handsome soup, I think. I picked those because they were the easiest one to get started. I haven't done any performance check to make sure that this one is faster than the other. Just keep that in mind. And right now, because I'm running it in memory and I don't want to start filling up my memory with crap, I'm just going to take the first 10 links that come out of a page and just append those to the queue. The process URL worker is the thing that, let me see, gets the set of visited URLs, gets a function that adds a link to the queue, the worker ID, and the text. This is the actual worker that I'm going to be running in the worker pool. The value that is coming out of that queue of work is the URL and the worker ID. All of these arguments are partially applied on the construction of my worker pool. I go and perform the fetching of the links and whatnot. And once I get the links, I add links to the queue, and every worker does that, right? And the web crawler is where I wire everything together. I have a manager for the HTTP client request. I have a beginning URL, a start URL, and I have a number of workers I want to execute. I just say, okay, how these workers are going to execute is through a TBQ. And I'm going to make this TBQ be the number of workers multiplied by 100 to give it like room. And then I'm going to have the visited set ref being in memory. Get next link is going to be reading from the queue. Add link is going to be writing to the queue. But the implementation details of how those queues are managed is something that the worker doesn't need to know. They just need to know that they need to perform a side effect. They don't need to know that it's a TBQ. So I'm partially applying these guys over here. I start by adding the start URL, and then I do a worker pull spec, the function that we just seeing a second ago, where we say, okay, we have a web crawler. The restart strategy is 1 for 1. If one of the workers fails, that doesn't necessarily mean that I need to kill all of them, just one of them. We have some parameters for the supervisor that can customize how the supervisor fails. What happens if a worker keeps failing over and over again? At some point, it doesn't serve any good to keep that not racing up into the supervision tree. So I say, I want to, if in 5 seconds, I get number of errors being equal to the number of workers divided by 2. So if I get, say I have 10 workers, and I have 5 errors happening in a period of 5 seconds, you're going to raise that up. What does that mean? Supervisor is going to kill all the supervised workers, and it's going to race up to the parent supervisor. The parent supervisor has a similar strategy to this. Say, oh, it hasn't failed once, so don't worry, I can restart you again. And it goes and does it. This is where static supervision trees are really useful. Because as soon as the supervisor says, oh, I'm going to restart the supervision tree, you don't need to do fork worker again. You just have all the definition of the workers statically on your supervisor, and it just goes and does it. Builds everything again. So these are the settings that I'm doing there. Supervisor intensity and period seconds. Then I'm getting the pull new work is get the next link. The worker name prefix is crawler. The number of workers is worker count. How you process the action is process URL worker, the one we were looking at a second ago. And the partial apply arguments, manager, visited sets, and add link. If we look back at the signature of the function, all those values are partially applied. The only 2 values that the worker pull API is giving you is the worker ID and the actual job that is pulling, which in this case is text. So I'm just fixing it to be a text. And then I do the main, which just does a for kappa task with the crawler spec and debug me the state of the crawler, join the kappa task thread, and away we go. Right? So what are the different error handlings that are happening here? Can someone give me a quick summary of what they understand so far?
Well, if there's a worker thread that dies, then the supervisor will restart it. But if you have, within 5 seconds, you have half of that supervisor's workers fail, then it itself fails, and that causes its supervisor to restart the whole
tree again.
Yeah.
What happens, like I did this arbitrary decision where I just saved half of the workers. What happens if it's the same worker failing multiple times because there's a domain that is down? There's different design strategies here that we need to consider, right? Like this is really naive because each domain, like if I'm having 500s from the same domain, it's probably likely if I keep requesting to that domain, it's going to fail, right? And my supervision tree is going to barf. So the supervision tree is not enough in here. One other thing needs to go down. What happens if the server is really slow? What happens if every request takes me 10 seconds and all my workers are dedicated to that same domain? Oh, I'm asking. Any ideas?
Queue is gonna step up.
Yeah, it's going to halt, right? And then you're going to be like, why is my worker not doing anything, right? What happens if I'm running a database server and 3 other processes in the same machine?
I can slow all the processes down.
Is there anything there that makes you believe that memory is important? How are we keeping visited set? The visited set.
It's the IRL, right?
Yes. So that keeps growing, eh? And what happens if, well, I have 32 gigs of RAM, that's not a problem. Okay, yeah, but what happens if your machine starts to get like saturated, right? All those things are things to consider, and there's strategies for that. There's anti-pattern, like those are common anti-patterns that are really easy to go through, and there are ways to mitigate those things, and those are the next things that we're going to be talking about. But let me see. What's the next exercise? Oh. Okay. Producers, consumers. So this is the project we're going to be playing with. It's not necessarily a project where you need to do something in order to make it work. It's a project where I want you to tweak it out and see what's the behavior of what's going on as soon as you change things. So welcome to my life. Let's go through. Okay. So we have a main application where we have a root supervisor called producer consumer. And I have a writer supervisor and a reader supervisor. And the writer supervisor and the reader supervisor are going to supervise writers and readers, respectively. We have a TQ that is shared among all the supervisors and among all the writers and all the readers. And the writer one is going to keep account, and anytime a number is multiple of 5, it's going to say, hey, reader, fail. And in case it's not mod 5, it's going to say, hey, this number I'm going to write this number. And the reader is going to say, if I get an error, I'm just going to throw an error myself. If it is not, I'm just going to say receive, right? And I'm going to sleep for a second and increment the number in. It's really simple. The way we create the supervisors here is by building a supervisor's options and saying the process list to be a list of writer specs from 1 to 10 and a list of reader specs from 1 to 10, and away we go. So why don't we run this thing and see what happens? So Okay, if I do that, oh, there we go. So this is happening. We have a bunch of senders sending, but no readers consuming. Why? If you read the code, what do you think we could change to avoid this behavior? Why are the readers not being restarted? Anything that looks suspicious in that code? Yeah. So we have a worker strategy where we say that we don't care about the outcome of the worker, if it fails or not. If I change this to permanent, what will happen? See a bunch of received, even though there's failures. Oh, still going. And Capataz is reporting where's the errors happening, what thread fails, but things keep going after the fact. What other things can we tweak here? Why do you feel curious? Where is your oyster? By the way, if you want to know what options you can set here, if you go to package, Capataz, and go through in here, lenses to modify options, you have all of them in here. Supervisor intensity, supervisor period seconds, supervisor restart strategy, supervisor process spec list, process termination order. So what happens when you're doing an all for one, or one for all, sorry? You want to kill them from right to left, from the most recent to the less recent, or from the least recent to the most recent. That's what termination order allows you to manage. If I want to have a callback when an intensity is reached on a supervisor, because I want to do some side effect, that's there. When a failure happens on a supervisor, you have worker on failure. When a failure happens on a worker, I want to do something else. When a worker completes successfully, I want to do something else. When a worker terminates because of supervisor restarting it, I want to do something else. Like workers that are stateful, I keeping a state somehow on an IRF. If I put these callbacks in there, I'm able to manage that IRF. Yeah, there's a lot of things you can play with in here. Like what happens if we change the intensity of the to always, like the supervisor always fail as soon as we have one error. How do we do that? So we have the reader. The readers are the ones that are going to fail. So I want to set up in a way that the supervisor is always likely to fail. And it becomes the responsibility of the root supervisor to restart it. How can I do that? So we use lenses for setting the attributes. If I want to add a new one, I just do a dot and set, and the attribute that I need. So I know I want to make sure that as soon as I have an error, it's just sparse. So supervisor intensity, you can just put 0 in here. See what happens. Oh no. Supply to too few arguments. Oh, of course. It's here. Oh, there we go. If I go and stack build that. and I run it. Okay, let's just stop it for a second. Let's go up. See the history here. Okay. So, telemetry is a lot, eh? Which keeps going. So, a bunch of things happens. Each of the readers gets an on failure call, because as soon as a supervisor that supervises all these workers fails because of an intensity reach, all workers are going to die, always. So you see that all of them have a report on failure. Reader 10, okay. And after they notify you that all the callbacks were executed, it's going to tell you it failed with this error. Fail, just the error fail. And it's going to tell you for all of them. And then the readers, let's see, what else is going on here? Okay, fail, 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 error, fail. It tells you that the supervisor readers change from running to halting. And tells you supervision started, termination of its children. And it tells you the reason. Supervisor intensity reached. This is the process ID, this is the process name that caused it. And then starts to terminate all of them. Supervisor terminated process, terminated, 5, 6, 7, 8, 9, 10. Then it tells you worker on termination for most of them. Supervisor finished termination of its children, meaning I already killed all of them. I'm changing the state from halting to halted, meaning that supervisor is no longer running. And then it calls the on failure callback of the supervisor. And then it reports it failed with error. This is the error. And then the supervisor reader starts again. Starting all of them again. And tells you, oh, it's initializing to running. And later on, it tells you the supervisor restarted failed process. The producer consumer root supervisor restarted the reader supervisor. Right? And then it continues as nothing has happened. If the errors keep happening on the middle layer supervisor to the point that it reaches the intensity of the upper supervisor, it's going to keep going up until the point that it fails everything. Right? But why middle supervisors are good? Huh?
Middle management.
Middle management. It containerizes the errors. If a part of the system is failing, as long as you have a supervisor of supervisors, it's going to say, okay, yeah, I know that's failing, but you're not going through the intensity that I'm registered to manage, so I'm going to keep restarting you as I go, right? What are sensitive values for intensity and the time between intensity? That's a matter of experience. There's no one recipe to make it right. You gotta see how your system behaves on different error scenarios and put the supervision restart strategies accordingly, right? Do you feel it's productive time to play with this example and try to understand a little bit more? Or you want to take a break and then continue with the rest? Just want to know.
I'm really doing great.
Yeah, okay. Great. Yeah, we have 2 hours left. An hour and a half. Well, it's 3 or 5. Let's take a break. Let's take a break no matter what. Let's tweak this this project for 10 minutes or so that you start playing with different settings, read the documentation, go through, try to write things. If you have any questions, let me know. And then we're going to start going into other strategies to solve the problems that I was asking a second ago.